This is a tutorial of the Dispersive Virtual Reference Analyzer from Inometrix. To start the software, click on Start, and then click on Dispersive Virtual Reference Analyzer. This opens up the software. You'll notice on the front panel that there's a left side to the controls and a right side. On the left side, we have the pre-runtime controls, and on the left we have runtime controls. And there are multiple tabs to go through during runtime. Under the scan parameters, we have start wavelength, stop wavelength, and output power. Please check your manual for your tunable laser to find the valid ranges of these values, as we do not control or limit the values that these can take, so that the system is compatible with multiple tunable lasers. Under the TLS port, we have the GPIB address of connected instruments. To refresh, please click on Refresh, and it will look for new connected instruments. Under the TLS mainframe, we choose if we have legacy, Keysight, or Agilent A-series tunable laser sources and mainframes, or current B-series tunable laser sources from the 81600 series of tunable lasers. This control here depends on the model of the virtual or dispersive virtual reference analyzer that you have. For this particular piece of software, we have controls between the CNL band channel and the O band channel. If you have only one channel, this radial selector will not show. So we'll select those. You can select these options here. Under measurement parameters, we have number of points and configuration. Under the number of points, we have this means the number of points desired in the dispersion curve, so the first and second order dispersion curve, to be measured using this instrument. Now, what happens is that the range set up in the range tab later on will be divided by 50. This number can decrement if there is an error in the measurement at any point. So what happens is that in dividing the range into 50 points, if the system does not get a good or clean interference pattern or an acceptable interference pattern, it will try up to a maximum of 10 times between points to get a good scan or a clean interference pattern. If it has tried 10 times and has failed, it will simply decrement and move on to the next point. So that's the number of points here. Under configuration, we have Fabry-Perot. So this is our typical setup for a virtual reference measurement, where we use a fiber, the facets, the front and end facets of a fiber, as reflection points to obtain an interference pattern. Alternatively, you can use a coupler, okay, and use a Michelson interferometer configuration. That looks exactly the same as, so an unbalanced Michelson with an imbalance of length L looks exactly like a Fabry-Perot with a fiber of length L, mathematically. You can also have a Mach-Zehnder configuration where you have two couplers attached to each other, and on one arm of those couplers, so first of all, they're balanced in length, so the two arms of each coupler, they're balanced, and on one arm you place your device under test, and you have an unbalanced Mach-Zehnder. So that's that one, which can be virtually balanced using the virtual reference. Another option is a bulk element, so a fiber break grating and reflection can be measured, and that's another configuration. So these are the possibilities. Under scan, that just starts the tunable laser to sweep and produce an interference pattern under the raw scan. I don't have a tunable laser connected, so I can't do that right now, but once you have that interference pattern, you can save it for later processing, so you can do multiple dispersion measurements on the same scan. And then we have load and quit. So what I'm going to do, I'm going to load the results of a previous scan, and I'm going to choose an 11 centimeter length. So we have a pigtail that's 11 centimeters, and it's SMF28, and press OK. So this is the interference pattern that was scanned using a Agilent 81600 series tunable laser. It's the B series, option 200. So we have a 200 nanometer bandwidth range here. We can reduce that if we like. With these sliders, we can reduce the maximum and minimum wavelength. I'm going to use the full scan, and as you see, we're going to need it for this 11 centimeter length fiber. So the smaller the dispersion length, you're going to see that you need more bandwidth to measure. So anyway, we're going to look at, although this scan doesn't need to be normalized or filtered, I'm going to show this functionality. So when we click on normalize and apply FFT filtering, when I press OK, the software will advance to filter and the normalize tabs. If they're not clicked, it simply advances to the balance and fit tab. But I want to show the functionality here. So here we have the original interference pattern and the result of filtering. So the filtering happens over here from these sliders. So these sliders, by sliding these sliders over, we're removing parts of the frequency. So I just removed here the DC component of the interference pattern. So you see the DC has been removed. Now see there's a reflection across the 0.5 sampling frequency, the half the sampling frequency, and this information is just repeated on this side. So it's duplicated. So by removing it, it doesn't affect the inverse FFT, so it doesn't change the interference pattern. So I'm just going to remove it, and all the information is encoded in the peak here. All of the dispersion information, because it has a width, it's not a single peak. It has a dispersion because the interference pattern, the phase or the period of the peaks, between the peaks, changes as we go from the low end of the interference, or the lower wavelength, to the higher wavelength. Anyway, I'm going to press OK, and we're going to move on to the normalization. What happens here is that, you see this window size, we have a moving window of 50 points, peak points, or we call valley points, I guess you can call them. But what we're doing is we're averaging them, and we're dividing all of these values by the average value, and that just basically normalizes the interference pattern between 1 and -1. So we can change the window size, but using a larger window size will just make the window size larger. You may have more noise on top of the curve with a larger window size. Anyway, I'm going to leave it at default because that seems to work very well. So I'll press OK. And we're moving on to the balance and fit. So first we do what's called a coarse balance. And what we want to do is we want to get a peak produced. We want to increase the number of points in our FFT. And so this FFT happens at actually the center of the scan range. So we're gradually increasing the number of points in the FFT, and we're getting a peak. Okay, this peak has a width because of dispersion again. Okay, because the period is changing. But we want the average period at the center of the scan range, because that's going to give us some information on the group delay. Okay, so as you see here, as I change the number of points in the FFT, I'm balancing, quasi-balancing, or coarsely balancing the interference pattern. Now I need to do some fine balancing here. Now what I want to happen is as I move either of these two arrows, I want to see that the period is increasing, because that means I'm getting closer to what we call the balance point, where the group delay in the simulated virtual reference is equal to the difference in the group delay between the phase fronts and the DUT. So for example, the group delay of if we have a Fibro-Perot interferometer, the group delay difference between the two reflection points. Okay, so as I advance, I'm going to get the period is going to increase, and I'm going to approach this point of symmetry. Okay, this balance point. I'll explain what I mean by that in a second here. You see, the balance point, it's where the frequency increases, or sorry, the period increases, and then it begins to decrease again. Okay, so that's this balance point. You're going to see that the period is going to start to decrease as I go in this direction. Now, in order to make a dispersion measurement, I need at least 2 peaks or 2 valleys. Okay, 2 peaks or 2 valleys on both sides of this balance point. If I don't have that, I can't make the measurement. Now, before I can take the measurement, I need to fit. I want to filter out this high frequency interference. So what I do is I do a spline fit, and I increase the value of this spline fit parameter until I have a good measurement. Now we're going to do this again in a second. Now here's where the dispersive virtual reference, so a virtual reference with dispersion, comes into play, where it's useful. So the dispersion of the virtual reference, it's linear. The second order dispersion is linear, so it's basically a line. It's with no curvature, and this can be used. So basically, the reference with dispersion can be used in this particular case. See, we don't have very many points, many peaks or valleys in our interference pattern. See here? So we can't really make very many measurements. The bandwidth of our results will be very small. Also, if we may not even get a single measurement because we don't have enough bandwidth. See, the number of peaks and valleys on both sides of the interference pattern is very small. So if we want to be able to make larger bandwidth measurements, or actually make a measurement, we need to compress the distance between the peaks and valleys on both sides of the interference pattern. And we do that using this using a dispersive reference. And this dispersion is controlled by what's called a compression, or it can be a decompression parameter as well. And by changing, let's say we make this K value 3000. Now what's the significance of the K value? Well, K divided by the speed of light is the dispersion length of the virtual reference. So by changing this value, we get a dispersion length. So now we have a 0.01. So the dispersion length of our virtual reference is 0.01 picoseconds per nanometer. And by using a dispersive reference with this dispersion, we effectively compress the distance between the points across the center of the interference, across this balance point. Now, the next step is to increase our spline fit parameter, okay, until we have good contrast between the peaks and valleys on both sides of this balance point. I also want to do one check. I want to see if a positive value of K has higher dispersion than a negative value of K. Okay, so I'll just do a quick check and see if the compression is greater. It's about the same because the device is quite small, but I think it's a little bit bigger, more compression with a smaller, a negative value of K. So that's good, and we can use positive or negative. It doesn't really make a difference in our measurement. But I like to see the device is SMF28. It has positive dispersion, so I like to use a negative dispersion for the value of the dispersive virtual reference, because it gives higher compression for the same magnitude. You can use either. It won't make a difference in the results. Okay, so we have our interference pattern. We have the spline fit. There are many values that the spline fit parameter can take on that are equally valid. We just want to make sure that it's not too high, that points are we're locating peaks and valleys where none are. We only want one peak and one valley, so one point for every peak and 1 point for every valley here, and we want to try to remove any multiple points from the center. Okay, so this value is good. We don't want it too small that we lose information from the stuff. If the spline fit parameter is too low, we don't get very many points on the sides. If it's too high, then we get points between the peaks and valleys that are not actually peaks. Anyway, so that's how we do it. We'll just leave it at some value like this. There's a wide range of acceptable values. Interpolate spline, it's if we want to increase the number of points in the spline, if for any reason we need to do that. Here we have about 2 million points. So the resolution, the wavelength resolution on the location of the peaks and valleys is quite high. It's sufficient. So we're not going to do that. You might want to do that if we had taken a smaller bandwidth range and we have less points in our scan. So anyway, so that's that. Now, if we wanted to manually input our dispersion length, we could do that. See, if I click on, if I put a check mark here, I can change this value to whatever I want it to be. Right? 484, let's say. See, and I'm changing the value. Okay. So that's that. Once I have this set, I just press OK, and it will advance to the range tab. Now, how does this work here? We could automate the range measurement. So this range basically is we determine the length, the minimum length and maximum length, so that this balance point, this center, has at least 2 peaks or 2 valleys on each side of the center point here. So we're going to reduce it. If we reduce the length here now this min OK tells me that it can make a measurement using this interference pattern. So it can't, right? So I'm going to move the balance point here. I'll move it to the left, and now it's okay. It can make this measurement. This is the minimum length of the dispersive virtual reference, simulated length, and then I'm going to do the same thing for the maximum length. Now I could do this. This can be done automatically for me if I click on that, and once I press OK, it will automatically find the balance point. I like, for the control that it allows, I like to do this manually, but it can be done. It can be automated. Now, so we've done that. Now, accept patterns with noise on the center peak. Well, if there's if the spline fit parameter was a little bit higher, you might have 2 points here. So this just adds flexibility to the system, but by default it's not checked because it discriminates against anything with potential noise. So it gives you better lower scatter if you don't click it, but it just the flexibility gives you more flexibility if you click this to accept more different types of interference patterns. Okay, so what's include effect of third order dispersion? Well, if we have this by default checked, because we include in our calculation of the second order dispersion, we include the third order dispersion, and the third order dispersion is the asymmetry. Okay, there is if a device under test has third order dispersion, the interference pattern will be asymmetric, which means that the separation between the peaks on one side will not be exactly the same as that on the other side. Okay, now including the effect of third order dispersion can add some noise to the second order dispersion measurement. So the only time where, well, the benefit of unclicking this is that you get smoother curves in your second order dispersion, but you can only really do that if the device under test has very low third order dispersion. and for example, in this case, in this device, it's SMF28, and it does have very low third order dispersion, so there's no asymmetry, and we could unclick this without change to the results. We include it even though it increases the scatter slightly, because it just gives us higher accuracy in the curve. Now, how does this work? Maximum deviation in the fringe period at the center of the scan and at the edges of the scan, and then minimum number of peak and valley points in the calculation. Well, okay, so all of these controls here can be left at their default to the novice user. Now, if you want to change them to improve the scatter in your results, you have to understand how they work. So how do they work? Okay, so when we measure dispersion, we're measuring the period between peaks and valleys, or peaks. Okay, we're measuring period. We're getting our dispersion information from the period of the entire scan. So the thing is that some interference patterns can have noise, which means that we could detect a peak where none exists. We could detect a peak between a real peak and a real valley. So how do we deal with that sort of a situation? Or even in the longer wavelengths, there could be errors in the location of the peaks. So how do we deal with that situation? Well, what we do is we monitor the changes in the periods. And if the change is greater than a certain value, which we set, then we know that there has been an error. So it's picked off a peak where none exists. Because you're going to see that you're going to have a change from here to here of 10 nanometers. Here to here would be 9.5 nanometers, let's say. And so that's less than this deviation. But if there was a peak located here, you'd see a point, or maybe 2 or 3 nanometer period, and then a 12 nanometer period, or something different than that, or larger than that. Then what would happen is that you detect that there's a change in the fringe period, and when the change is greater than 1.5, you know that there's a problem, or greater than whatever value you put here. So what happens is the system cuts off all the peaks and valleys before that error, or if it's on the other side of the balance point, after that error. Now, how does this work with the minimum number of peaks, peak valley points in the calculation? Well, in order to make a measurement, we need at least 5 peaks and valleys, peaks or valleys. So we need the center, and then we need 2 peaks on either side of this balance point. Okay, so, but if we cut off points from this using this tolerance, we could end up with less points than desired. So let's say that we want to ensure that all our measurements of second order dispersion have at least 10 points. Now, having more points obviously gives us a better measurement. There's less error in our measurement. So if we increase this value, we reduce the error in our measurement. But if our tolerance is too high, we may not get any points. Right? So basically, this controls what we will tolerate. The errors that we can tolerate. It eliminates points that, error points. But this ensures that we have enough points, or a certain number of points, minimum number of points in our dispersion measurement in order to accept that measurement. Okay, so that's how these two work together. Now, why do we have a variation between the points at the center of the scan range, or the changes when the center is near the center of the scan range versus when it's at the edges? Well, when it's at the center, notice the spacing between the period of these peaks is very small here. So within this scan, we have peaks that are very close together. But if we if we're near the center, we have higher period peaks. So naturally, when we're at the edges, we may want to increase our or decrease our tolerance, okay, so that we can cut off any noise in this part of the scan. Okay, so if there's any noise, it just cuts off the rest. But we have to still ensure that we have at least a minimum number of peaks or valleys in order to make our measurement. Okay, so anyway, you can automate the measurement. I like to control it manually. That's my way. Well, you know what? Let's show the automated measurement. And so we're gonna say okay, and we'll let the system find the balance point. It starts from scratch. It finds the endpoints, and so here it's doing it automatically. And we're gonna go with the default five number of peaks. And here it's scanning. It's in the sweep. It's in the sweep tab here. So LV is being advanced, and the center of the balance point is being advanced as well. And we're producing a group delay curve, a group velocity dispersion curve, and a dispersion length curve. There was an error point at one of the endpoints here. So anyway, when you have an error point, you know this is obviously to be thrown away. Now, once we're done, we can export our results. Let's say I'll create a folder here. We'll call it results, and then we'll click on the folder, and we'll just say test 1, let's say, and press enter. Now we can always go into that folder and change it into a text file by adding the .text to the end of it. We can do that, and anyway, I can go into here. It's in the Inometrix folder here under demo scans and results. If I want to open it in Notepad, I just put a .text file, and then Windows will recognize it as a text file. Anyway, this file is tab delimited text file. It can be imported to MATLAB. It could be imported to LabVIEW, Excel, etc. Here's our point that was an error. Was produced. We have an error point here. I can just remove that from the results here. Anyway, I'm going to leave that for later. And that's it. So now, if we wanted to quit, we just press quit, and the program will exit. Thank you very much. I hope you enjoy your dispersive virtual reference analyzer.